Section 12.2, Electronic Structure of Material. All right, so I need to remind you of something that everybody hates. This was the molecular orbitals. So let's look on the left. I've got a yellow box with a 2s and a blue box with three rooms at the same energy level, and that's 2p. So the 2s electrons were low energy. The 2p electrons are at higher energy. Okay, so remember if you make a bond between two atoms, the electrons are going into regions of space, or at least they're thought to go into regions of space, called an orbital. And an orbital holds 2 electrons. So in the case of this picture, I can see that let's pick silicon. Silicon, we're going to talk about it later as a semiconductor. So with silicon, you're going to have, here's 2s, so I've got an up and down. This one had 2s, that's up and down. Silicon has 4 valence electrons. So remember Hund's rule, I have to give it its own room. I need a better pencil. Okay, so I've got an up and down on the left and up and down on the right in the yellow, 2 ups and 2 ups in the blue. Okay, so when I put those together, I simply take one of each. So I get an up and down in the bottom, an up and down in the top, so that's an anti-bonding orbital. And then here I've got a down and an up here, and then 2 ups. Okay, so in this molecular orbital, I've got the sigma 2s is full, the sigma star 2s is full, the sigma 2p is full, the pi 2p is full, but the pi star 2p is unoccupied. Okay, that's open, so electrons could go in there. And then the sigma star 2p is also open. So I just want to give you this. This is analogous. This is the idea that electrons live in a certain place. They occupy a certain place, and if given the sufficient energy, they could go to a different place. All right. Let me change my pencil just a bit. Okay, and see if I can. All right. Let me give you a different picture in your head. If you remember the Bohr's atom, okay, I had some kind of a nucleus, and then I had an electron. Remember, he did the hydrogen atom, so it was 1 proton and 1 electron. And if you gave that electron energy, let's say that you had radiation on it or light hits it, you can get that energy to an excited state. It can move to a higher orbit than it normally occupied. Okay? In order to go from here to here, it takes energy to do that. Okay? Energy has to go in, and then when it's up at this higher excited state, it's energized, and if it were to ever drop back, that's when it will emit a photon, if you remember the Bohr's model. Okay? I want you to put these two kind of things together. Electrons occupy a certain place, and if given enough energy, they could occupy a higher place. All right, that's all I need you to know for the beginning, okay? They occupy a lower place, and they can, with energy, occupy a higher place. All right, so let's see what's the next thing. Oh, I need to erase this. I'm sorry. Okay. I've got smudges all over the place. Okay. Okay, so now we have this idea of a band. This is called band theory, by the way, and it gives everybody in the world a headache. This is not easy. This is hard. Okay? So let me kind of give you an idea. Remember when I did molecular orbitals just a minute ago? Okay, so 2 molecular orbitals are going to break apart into lower energy orbitals and higher energy orbitals. So here's one atom. There's no bonds there. But if I have 2 atoms interacting together, I'm going to have, remember the sigma S and the sigma star S. Okay, so they break apart into a lower energy and a higher energy. Well, if you had more than one reacting, remember the P's, they will have more orbitals. Okay, so let's imagine now I have 5. If I have 5 atoms interacting, I'm going to have 5 different energy levels. If I have 6 atoms, I'll have 6 energy levels. And so what is your idea here, or what we're trying to idea, is let's say I have 100. Okay, I have 100 atoms, then I'm going to have so many energy levels that they're so close to each other that it's actually, so I might occupy, remember our silicon, we had the bottoms occupied and the tops were available. This here was available. All right, so this is kind of this idea. If you have more and more and more, many atoms working together, you are going to have almost a band, okay, of open, so here's the open ones, and these are the occupied ones. Okay, so the electrons that are occupied where they belong, where they normally live, are down in this area, and then the ones that are open are at the top. Okay, so far so good, I hope so. Now let me just cut to the chase. What's going to happen is, in order to conduct electricity, if you're going to conduct electricity, you have to have electrons in these open spaces. There must be, you must have electrons that are free to move. And if they're free to move, then they can conduct electricity. All right? Now let me remind you too of one of the bonds. Let me move it up just a little bit. Remember to erase. Okay. Right. So let me come up here. I'm just going to get some empty space. So if you were to let me just remind you of metallic bonding for a second. Okay. Remember, you have individual atoms in that, let's say, a piece of copper that's conductive electricity. And all of these are positives in the inside, so there's a nucleus, and electrons around the outside. Okay? The difference with a metallic bond is the valence electrons from each of these individual atoms are in between. They're delocalized. They're everywhere. Okay? They're just basically free to move around. In fact, they're free to go around the entire surface of that wire. Since they're free, what's actually happening is that they're in already, just as a metal. Let me erase this real quick and I'll go back. They're as a metal, since they're a metal, okay, like copper or gold or something like that. Let me go back just a second. Okay. Do you see that they are already in this open? Those valence electrons are in the open chamber, and as such, they're free to move. Well, if they're free to move, that's electricity. Electricity is the movement of an electron through some kind of a conductor. All right? So movement of electron through a conductor. All right, so let's see if we can go any further. So in the case of a metal, since metallic bonding allow those valence electrons to be free, they're already free. Since they're already free, it's no energy to go into that unoccupied. So the bottom that's blue is called the valence. These are the electrons that are stuck in the atom. And then this top one would be the open. Not sure if it's called open or not. I'm very sorry if it's not. Okay, I think it's called the conduction band. So these are bands. All right. So you have the valence band and the conduction band, and it's open. It's free. And if you can get an electron in there, then those electrons that have been given that much energy. Do you see? It's more energy to go this way. So it's more energy to be in the upper box than the lower. If you can give an electron enough energy, then it now can be electricity. That electron can move in the wire. All right? In an insulator, you've got a big gap here. Okay, this is a gap where those electrons you have to give it a huge amount of energy to get it from here to here. So it's so much energy that actually it's the same amount or more energy as it would take to break the bonds of that material. So it's almost never going to happen. Under the weirdest conditions would it happen. Okay, so an insulator has no available electrons in the conducting band. Oh, it is conducting because that's what C is. C is conducting. So there's no electrons in the conduction band, and because of that, it's an insulator. It doesn't conduct electricity. In the case of a semiconductor, it's got a small enough jump that certain electrons can be given enough energy and you can get a little bit of conductivity. So a lot of this has to do with what's the temperature like, when is it going to be conductive or not. So let's look further. I hope I'm helping you. Okay, so the gap determines whether something is a metal, where there's no gap or it's even overlapped. A semiconductor is a little bit of a gap between a valence and a conduction band, and then the insulator is a huge gap, and so it's just not likely to happen. Okay. In your textbook, I'm sure there's a table that tells you what this is in electrovolts or kilojoules per mole. They can be converted, and it basically, if it's a certain amount, I think like a insulator would be more than 350 kilojoules per mole. A semiconductor would be between 50 and 300, something like that, and anything less than 50 would be considered a conductor.